Hello, myself Naveen Saini. In the course Electromagnetic Field Theory, today in the lecture 15, we will start the magnetic forces. So, in that, first we will recap what we have discussed till now. So, we have discussed about the Maxwell's equation for the static fields. Okay, so in that, we have discussed it in terms of the point or differential forms. We have discussed it in terms of the integral forms. So first in differential form, which is based on the Gauss law, that is del dot D is equal to rho. So this is the first Maxwell's equation. Okay, and we have derived this Maxwell equation differential form from the Gauss law, which is given as the charge enclosed, and that is equal to the flux lines. So that is D dot ds with the closed surface is equal to rho v into dv. Okay, so we have derived this equation from the Gauss law, which was psi is equal to charge enclosed. The second Maxwell's equation, which is in the magnetic field, so which is the del dot d b is equal to 0, and we have derived this equation from the this b dot ds is equal to 0. So what it says that there is no non-existence of the monopole in the magnetic field. Okay, so the integral form for this equation is b dot ds with a closed surface is equal to 0. So this is very important point where we have to specify this circle. Okay, so if we not make it the circle, if it is not a closed surface, then it will not be 0. Third Maxwell equation is del cross E is equal to 0. So we have derived from the Ampere's law. From the conservation of electrostatic field. So it says that E dot dl is equal to 0 for the closed path. So we have gone from A to B and B to A, right? A to B, B to A. So we have done it based on the total work done, that is equal to 0. Okay, so from there we derived this equation del cross E is equal to 0. Okay, so next was fourth, del cross H is equal to J. So we have derived this Maxwell equation differential form from the integral form, that is from Ampere's secretary law. So which tells H dot dl closed path is equal to I enclosed, right? So we have derived this equation. So this equation was based on the Ampere's secretary law, that is H dot dl closed surface closed path, that is equal to current enclosed. So we have derived this equation from the Ampere's secretary law. Okay, so next point in that is the magnetic scalar and the vector potentials. So in the electrostatic, we have discussed about the scalar potential, which we have denoted by the V, and the electric field is given by the minus gradient of V, right? So which is similar to this, we can relate to the magnetic field intensity with the two magnetic potentials. So first one is the magnetic scalar potential and the magnetic vector potential. So due to the presence of the charges, there is the potential which is exists, that is magnetic scalar potential, which is the same as we have discussed the electrostatic. But as the charges are in motion, it is accelerated or deaccelerated charges are there. So because of that one, it is moving in some direction. So there is the vector potentials also introduced into the magnetic field. So these two potentials are there, V, M and A. So in that magnetic scalar potential, which is same as the electrostatic potential, so here the relation is same, but we have to find the, based on this relation, where the magnetic field intensity H is equal to minus del into Vm, right? So the condition it occurs if J is equal to 0. So if the current density is 0, so in that way this equation will be same as the electrostatic field equation. Then for that we can use the Maxwell's equation. So when we use this Maxwell equation, J is equal to del cross H. So in that we can put in place of H, that is minus del Vm. So when we can put it, so this is again the same thing when we have the gradient curl of the gradient of any potential, so that is equal to 0. So this is the identity which we are very much aware about that. So the magnetic scalar potential VL Vm is only defined in the region where J is equal to 0. So this is a specific condition when there is no charge density present. So in that case only the vector scalar potential come into the picture. So Vm satisfies the Laplacian equation. So okay, so that is del square into Vm is equal to 0. So the condition is same, J is equal to 0, right? So it satisfies the Laplacian equation. Now when we have this definition about the magnetic flux through a given surface area, so for that psi is equal to B dot ds, right? So in the case of electrostatic, I am just giving the comparison along with it, that phi was equal to D dot ds when we have the open surface and we have electric flux density D. So similar to that, in analogy with that, we have the psi that is equal to B dot ds in the magnetic field. So when we apply the Stokes theorem into it, why we are applying the Stokes theorem? Because this is the open surface, and I said in the previous cases as well that open surface, that is, can be get it from the closed path. Okay, and when we have the closed surface, that is, we are getting the volume. Okay, so for this case we apply the Stokes theorem, and here we apply the divergence theorem. Okay, so here we have the open surface, so for that we can apply the divergence Stokes theorem into it. So before that we can use this B dot ds. In place of B we can write the del dot A into ds, and that is equal to A dot ds. So we are applying it here the Stokes theorem, right? So this is equal to Stokes theorem, that del cross A dot ds is equal to A dot ds. So here where the psi is equal to A dot ds, this is the total flux passing through the given surface, right? So for that we can get it, so we have to use the closed path from here. So when we have the closed path, that is A dot ds. So this is one of the example which we can go through it, that when we have the vector potential is given, magnetic vector potential A is given in the AZ direction, then calculate the total magnetic flux crossing the given surface. So first thing is the how to create the surface. So this surface is like that. We have the surface, vector flux lines are crossing into it. So how much flux is enclosed by this given surface? So that surface is defined by psi is equal to pi by 2 and rho is equal to 1 to 2 and z is 0 to 5 meter, right? So for that, again the A is given and we have to find the magnetic flux crossing the surface. So obviously magnetic flux is required, so means the B is required. Okay, so the formula which we have, that is B is equal to del cross of A. This is the formula for this, where the vector field potential A is given, then we have to find the B. Okay, if in the exam they is not mentioning the total magnetic flux, they are simply mentioning A is given and find the B. So automatically we have to be very much clear about this, that B is nothing but del cross of A, or the curl of vector A. So in this you can see that vector A is in which coordinate system? It can be into the cylindrical coordinate system, or this surface can be of your Cartesian, right? Because AZ is in both the cases. But the how the surface we can define, surface can be defined by phi is equal to pi by 2 and rho is 1 to 2. So phi is equal to pi by 2 means this is from the x-axis, this angle. Okay, so when it is from the x-axis, so this is x-axis, so here from here this is the 90 degree. So it means the one surface is lying at phi is equal to pi by 2. So this will be lying on the y-axis. So rho is 1 to 2. So this is the surface, rho is from 1 to 2. okay, and z is 0 to 5. So this is the total length is 5. So this is the surface which is created. So what we require, we have to find how much flux is passing through the surface, del cross of A. Okay, so as A is given the in the, because this is your cylindrical coordinate system, based on this we can see this is cylindrical coordinate system. So for that the del cross A will be del Az upon del rho into A5. Okay, so here we can put the value of A and we can differentiate it. In place of Az, just put the value minus rho square upon 4. So when we put it, then value will be rho upon 2 A5. ds is what? Ds we can define, we can take one element here. So this is the ds, so this is maybe the ds. Okay, so this surface is, because phi is constant, so d phi will not be there. So what left? Three parameters are there, rho, phi and z. So corresponding to that we have the d rho, rho d phi and the dz. So these are the differential elements in the cylindrical coordinate system. Okay, so this is the elements. So as I said, for this surface phi is constant, phi is equal to pi by 2. When phi is equal to pi by 2, so it shows that d phi will be 0. This obviously. So in this case will not be there. So the surface will be defined between this and this. So d rho and d phi. So d rho and d phi is the element for this. So this is the ds, that is equal to d rho and d z. Sorry, d rho and dz, because d phi is not there. So it means d rho and dz is there, and the direction of az will be, this will be a phi, right? So this is the a phi direction is there. So in this case we can find the b dot ds. Okay, so we got total flux, we have to find out. This total flux is the, flux is size, and b is the magnetic flux density. So this is the magnetic flux density which is required, but this one is the your phi. Okay, so this is psi. So b dot ds we can apply it from here. So in that case the rho is 1 to 2 and z is 0 to 5. So when you solve this, 1 by 2 and so on, 1 by 4, when we solving this one, 15 by 4 will be the value, and the solution for this is 3.75 Weber, right? So this is the way to find the total flux. So there is another method for solving this same problem, where method 2 we have to find total flux passing through this all the segments. So in that segment, so when you understand this, then psi 1 and psi 3 will be 0, but there will be a psi 2 and psi 4. So psi 1 and this is the psi 1 and psi 3 will be 0, because this is parallel to the y direction, right? So it, and the ds is in this direction. Okay, so when we apply this, then when we applying this, then the psi value will be the same, that is 3.75 Weber. So please work out on this. So this is the same method which we have used in the for the finding the flux lines. So now come to the forces due to magnetic field. So in that the forces due to magnetic field can be find out in different ways. First is the when due to the moving charge particle q in the B field. So when the B field is already existing there, and into it we are moving the 1 point charges, so what the force will be exert onto this particular charge which is moving into the medium. Second case is on the current element in an external B field. So in the previous case, in the first case we have the moving charge particle. In the second case we have any external closed loop, current element. That current element exists into the magnetic field, existing magnetic field. So what is the force into the current element we have to find out. The third case is the two current conductors. When we have two current conductors or two loops are there, so based on that we can find the what the total flux or total forces exert onto the current element. So this is the same which we have discussed into the electrostatic field. When the charge is moving into the existing electric field, then we found the what is the force exert onto that charge. Okay, now same scenario is here when we have already existing magnetic field is there, and we can find the magnetic force onto the different three cases. First is the moving charge into that magnetic field, second is the current element into that magnetic field, and third case is the when we have two current carrying conductors or the current elements. So what is the force exert between these two elements? Okay, so B is defined as the force per unit current element. So this is the definition for the field. So important point here is the already existing magnetic field is there. So here we have, when we have force, first case is forces on the charged particle or charged elements. So in this case we can see when we have stationary or moving electrons, so in that case the electric field will be exerted onto it. So force is equal to Fe is equal to Q into E. So second, when we have the magnetic force, so for that Fm will be Q U cross of B. What it shows that in the first case it shows that the Q charge into the existing electric field. Second case Fm is the Q charge is in motion with the velocity of U, and this is moving into the existing magnetic field B. Okay, so the source for this magnetic field is separate. Into it the Q charge is moving into with the U velocity. So in that case the total charge, total force can be calculated. So what is total force? The total force will be Fe plus Fm, right? Fe is due to the presence of the electric charges. So onto it the total field, total force will be Q into E. But when it is the moving into the magnetic field, then the force will be Q U into cross of B. So total force onto the particular charge which is moving into the medium. So in that way the total force will be Q into E plus Q U cross B. So Fm is perpendicular to both of U and B. Okay, so if the charge has the mass, so M, then in that case the force, total force will be what? So this force will become M into A, right? So this can be your M into A. So A is the acceleration, so this one can be defined as the du upon dt. So F is equal to M du upon dt. So here Q is so this is equivalent to Q, can be taken outside from this two equation. So what will left? E plus U cross of B. Okay, so this is the way to find the total force, and that is equal to M into du upon dt. So here the interesting point is to be noted, that is Fm is less than equal to Fe, right? So force, magnetic force is less than the electrostatic force. So you have to be very careful about that when you are solving the numericals. So the forces can be compared in this way. Second is the force on the current element. So where when we talk about the current element, so current element is nothing but that is I into dl. So in that given element, current carrying conductor, when we are taking the one of the element from there, so current into it is defined as the current element I into dl. So I into dl can be write as the, in place of I we can write the dq upon dt and into dl. So here we can rearrange these things. So in this way dl upon dt will be like this. So this dl upon dt is nothing but the u. So here dq into u is there. So the same, this current element I into dl can be defined for the case of the in the magnetic field. We can define it dq into u. So we can write the equation for the Fm or the Fm, that is Q U cross of B. So we can define this equation as the, in place of Q into U we can define as the I into L. So we can see that dq into u, that is equal to idl. So in place of q into u, we can define it as I into L cross B. Okay, so L cross B. So as for the closed path, the I is the current. So in this way, we can define the total force. So this total force can be defined as the Fm is equal to IDL cross B. Again, this IDL is nothing but this is the current element. When it is placed, this current element into the magnetic field, already existing magnetic field B. So what is the total flux, total force exerted onto this IDL? So this force can be defined as the Fm is equal to IDL cross B. Okay. So I think this point is clear. So in another way we can write this equation when we have the Fm is equal to this one. So if we have the force on the current element 2 and the magnetic field is exerted by the current element 1. So for this case, what will be the value? Then Fm2 is equal to closed path IDL. So this is nothing but this is the current element 2 on which we want to find the force and cross of B1. I hope this point is clear. What is the significance of this? There is a one current element 1 through which the magnetic field is already present, that is given by the B1, and we have another current element. So that current element is placed into the magnetic field of B1, which is the external magnetic field. So in this way, what is the total force exerted onto this second current element? So in this way, that is Fm2 is equal to I2 dl2 cross B1. So the same thing we can define in different way when we have the one of the current element 1 in which we want to find the magnetic field. So in this case, the equation will be Fm1 is equal to closed path I1 dl1 cross of B2. So what is significance of this? The significance is this: the current element, any of the current element, the source is generating the magnetic field into which the current element number 1 on which we want to find the magnetic field force, then Fm1 will be equal to I1 dl1 cross B2. So very important point to understand about this equation. Okay, so in this way, for this one we can erase this point. So here the another point is to be take care of about the when we have the surface current element, right? So this is the case of the surface current element, where the surface current element can be defined as when we have the different current elements and we are putting onto the surface. So this surface is defined as the surface current element or the surface current. So in place of IDL, we can write the K into ds cross of B. Okay, because IDL is equivalent to the KDS. So this is the surface current. So K is ampere per meter, which is the surface current element. Then third one is the Fm for the volume current element. So in the volume current element, in place of IDL, that is equal to KDS is equal to JdV. So here, this will be JdV cross of B. So phenomena will be the same, which we have discussed. Fm for finding the forces onto the current elements. So that current element can be point charge moving into the current element, or it can be surface current element, or it can be volume current element, right, on which we can find the magnetic force. So the important point is the B. So this B is the separate different magnetic field which is generated by the any other source. Okay, so this is not that source on which we want to find the magnetic field. So already existing magnetic field is there by the another source, and we are carrying the one of the element so into that magnetic field. So we have to find the force. Okay, so unit for this one is very simple, ampere per meter square, and we have discussed these things in the previous cases. So third case is the force between the two current elements. So here we have, there is no external sources are there. We have two current elements. So one current element will have its own magnetic field. Second current element is have its own magnetic field. So in that case, scenario is here when we have the current element number 1 here. This is the current loop or the current element number 2, and we want to find the force onto the current element number 1 due to the current element number 2. So it means so scenario is very simple. We want to find the force here due to this. It means the magnetic field we have to use from this loop number 2. Okay, so this magnetic field will be there due to the loop number 2, and we have to find the force on the element number 1. So the same scenario which we have discussed in the previous slide, same scenario we will apply it here. So as I said, the dF1, so this is the force exerted onto the loop number 1 or the element number 1, and that is equivalent to the I1 dL1 cross of B2. So this is the B2 is what? This is the magnetic field which is generated by this loop, right? So here, then if we want to find the total magnetic flux density, so for that we can write B2, that is equal to, for that one we require the B2, right? So this B2 is equal to this one. So this dB2 is equal to mu naught I2 dL2 cross AR21 upon 4 pi R21 square. So this is by using the Biot-Savart's law. So if you are very much clear about that, that will be very easy to understand. That was equal to IDL cross of AR divided by 4 pi R square. Okay, so when we have the B, then in this case B will be mu is equal to N, mu naught into N when we have the free space. So what we this equation is the same as we have dB is equal to mu naught into dH, right? So we can take it the dH from here. So when we take this, then in this case the equation will become okay, so this is the dH obviously. So this is the dH because this is the dH and this is the dL. So when we want the H, so in this case for finding the H we have to integrate this. Okay, then this equation will be like this. Okay, so we are using the Biot-Savart's law. R square. Sorry, this is the R. Okay, AR upon R square. So it will be R cube when we have the vector R divided by R. So here, from here we can find that dB naught from this one, mu naught into I2 dL2 cross of AR. So this is the equation which we are getting from there, 4 pi R square. So this is the Biot-Savart's law which we are using. So the important point here is to find the B2 first, right? So this is known to us. For finding this dF1, B2 must be known to us. So it would be helpful to use it by Biot-Savart's law. dB2 is equal to mu naught I2 dL2 cross of AR 21. So this is from 2 to 1 to 2 to 1. So when we put this value into it, so what we will do, we will again differentiate it. Okay, then we will get the dB2. So it means if we want the F1, so we have to integrate this equation. So when we integrate it, then F1 will be equal to mu naught I1 I2 upon 4 pi closed path dL1 cross dL2 cross AR21 cap upon R21 square. Okay, so similar to that, so this is the F1, the force on the loop 1 due to the loop 2. So opposite of that one, we can find the force onto the loop 2 due to the loop 1. Okay, so what will be the change? So change will be here, it will become the F2, it will become F2, it will be same, this one will be same. So here it will be only change will be AR12, and here it will be DL2, so this will become DL2 cross of DL1. Okay, rest will be same everywhere, but this will be the differences which will occur when we have the force, when we want to find the F2. So this is one of the numerical which you can go through it, where the scenario is here that we have the one current conductor, this one, and we have loop 2. And what we want to find the force onto the loop 2 due to the current element. So when we have due to the current element, it means the magnetic field will be generated by this current element I1. Okay. So this one current direction of H will be from this one. So when we look the magnetic field, so direction of magnetic field will be this one, everywhere. Okay. So magnetic field is there. So if I'm saying the magnetic field is F1 here, it means we have to find the force onto this loop. So we can take the segments for this complete loop. So the 4 forces will be exerted on these loops. So we are assuming the direction of F1 onto the loop. Segment 1 is in this direction, segment 2 is in this direction, segment 3 is this one, and segment 4 is in this direction. So when we can find the total force onto this loop, then in this way we can calculate, we can combine all these forces, and the total force will be F1 plus F2 plus F3 plus F4. So total force onto the loop, that is FL, will be equal to F1, F2, F3, F4. So we have to find the forces onto it. So first thing is, what is the requirement? B1 we have to find, right? So this is equal to I2 DL2 cross B1. So B1 we can find for the infinite line, that is equal to mu naught I1 upon 2 pi rho naught into A5, right? So this is a value of B1. So this is, we can find when we have the infinite long current conductor, and the magnetic field we have derived by the Weierstrass's law, mu naught I1 upon 2 pi rho naught A5. Okay, so B1 we have to use all the time from here. So B1 is, we can use it. So this B1 will be everywhere. Here B1 will be there, B1 will be here, B1 will be here. Everywhere B1 will be here. So we have to use this B1 and we have to find the force. So first is the force on F1. So F1 definition is I2 DL2 cross B1. So we can use this B1 is the same as we have this. And here this F1 element is in this, because this is the direction of I2. So here element will be I2 DL2. So this I2 DL2 we are using here. So what is the direction of DL2? DL2 is in the direction of Z, right? So we can take in place of DL, that is DZ, right? So I2 DZ, AZ cross U naught I1 upon 2 pi epsilon naught A5. So here the limits of Z, we can take it care of. The limit of Z will be from here to here, because this is a segment. So this length is nothing but 0 to B. Okay, so this is the length for 0 to B. So we are taking it because direction is from in this direction, positive Z direction. So that is why we are taking the limits for Z at Z is equal to 0 to B. So when you are solving it, then we will get F1 is equal to minus mu naught I1 I2 B upon 2 pi rho naught A5. Similar to that, we can find the F3. So when you're solving this F3, so in this case the direction is in this direction. So obviously this is Z is equal to B, 2Z is equal to 0. Same thing will be there, but the difference will be occur. There are B is up from here to here. It was the rho naught. So now it is from here to here. So this is a rho naught plus this length. So this length is nothing but A. So B1 we can use this way. Dz is same, the limit is B0, B to 0. So when we are solving this, then F3 will be opposite of F1. Okay, but the case is here that in place of rho naught we have rho naught plus A, which is repulsive. Okay, so next is F2. So in this segment, we have B will be from here to here, right? So which is varying, rho is varying, so rho will vary from this length to this length. So that is why we are taking the B is this one, and the limits will be rho naught to rho naught plus A. So up to here this is the rho naught, and up to here this is the rho naught plus A. Rho naught is this one and this one is A. So when you're solving this, then F2 will be this one, this much, and similar to that F4. For the F4, the limits will be from here to here. So this is the rho naught plus A to rho naught. So rho naught plus A to rho naught, 0, A5. So this is mu naught I1 of A5 on 2 pi rho. So here the rho is also varying, right? So rho is varying from here to here. So that is why we're taking the limits from rho naught to plus A to rho naught. So this is the parallel parameter which we are getting it, okay, but opposite of in the parallel, right? So forces are parallel but opposite to each other. So total force we can get it when we combine all F1 to F4. So for that one F1 will be mu naught I1 I2 B upon 2 pi, and this is 1 upon rho naught minus 1 upon rho naught plus A minus with the minus sign. So this minus sign is representing that is the attractive force which is trying to draw the loop towards the wire, and the force Fw on the wire by Newton's third law, that is minus of Fl. Okay, so this is the way how to derive this derivation for finding the force onto the loop by existing current carrying conductor. So I hope this point is clear to all of you, and you can go through the magnetic forces to understand very deeply. If you have any doubt, please you can comment on the chat box. Thank you very much.